Hello students. So welcome to the third lecture of group theory. As you can see in this lecture, you will be actually seeing me presenting, seeing me giving the lecture so that you won't have difficulty in believing that I am giving the lecture. And you'll have the same feeling like Google Meet, except that this will be an offline. I mean, you can watch anytime. This will be a YouTube video of the same. And I'll tell you before that my videos will be longer than usual because of two reasons. First one, two things I'm trying to cover. First one is that I'm trying to cover whatever we have discussed last time, as we do in the offline classes in the Google Meet, what we have discussed. And this is because many of you may have missed the Google Meet, or you have poor internet connection, or you may not be able to follow whatever I say in the Google Meet, uh, maybe due to some or the other reason. So I'll try to cover the same also here. So that is the first reason. Second is I'll be giving notes and demonstration. I'll be presenting the whole lecture for the next Google Meet, including the exercise to be discussed in the next class. So because of this, my videos will be longer. So please bear with me. You might need a good amount of data connection. I hope you will be able to manage. Okay, so let us recall what we have seen last time. Uh, what we have been discussing for past two lectures is we are interested in such a problem as this example we have seen. S is a non-empty set. It is any set, right? S is a non-empty set, and G we have taken here. G equals to AS. It's a special notation. AS. This is a set of all one set of all one and onto functions from S to S, or we say that set of all bijective functions from S to S, or it is also written like this: set of all one functions. This is another way of writing from S onto itself. Right? This is one another way of writing. So set of all one functions from S onto itself. So this means that this is the set of all one and onto functions from S to S. Right. So in the last lecture we have seen that this AS is a group with respect to composition of two functions, operation of composition of functions. And the two exercises that we listed last time, what we are interested in is in the cardinality of AS, depending on the cardinality of S. If S is a finite set, on a finite set, how many one and onto functions we can have? Finitely many only. But then, what is the relation between cardinality of S and cardinality of AS? So this we have seen last time, that if S has only one element, so if cardinality of S equals to 1, then cardinality of AS is also 1. Only one element, only one functions we get. If cardinality of S equals to 2, then cardinality of AS equals to also 2. We have two functions. Suppose S equals to AB, A comma B. Then we have two functions F1, which is identity function. A goes to A and B goes to B. And another function we have F2, which interchanges this two, sends A to B and B to A. This is what we have seen last time. And yes, now this interesting problem, which we'll see, which we have seen last time. This video is in advance, so pardon me for that. Uh, so when S equals to cardinality of S equals to 3, that is, suppose S is this set. Uh, so let me write A, B, C, right? So if S is this, or let us write 1, 2, 3, for because that notation will be using in future. So now let us, instead of just writing general x1, x2, x3, or ABC, we just write 1, 2, 3. So 1, 2, 3. Right? So S has 3 elements. Now how many functions, 1, 1 and on to functions, we can give from S to S? So that is a question. So obviously let me try to list here. So F1 is, I'll list identity function 1, 2, 3. So 1 goes to 1, 2 goes to 2, and 3 goes to 3. Right? So this is identity function. Remember, we don't have constant function here because we are looking for 1, 1 and onto function. So we cannot have 1 goes to 1, 2 goes to 1, 3 goes to 1. Such type of functions are not allowed. We are looking for all 1, 1 onto functions. So let us take F2. F2, so 1, 2, 3. So let us say 1 goes to 2, 2 goes to 1. And then 3, obviously it has to go to 3. Right? 1 and 2 are interchanged, and 3 as it is. This is F2. Now 3 as it is. So here also similarly we can have F3, where we can have 2 as it is, and 1 and 3 are interchanged. So 1 goes to 3, 3 goes to 1, and then 2 goes to 2. And similarly now F4, 1, 2, 3. So here now 1 is fixed, and then 2 and 3 are interchanged. So 2 goes to 3, 3 goes to 2. So these are the 4 functions. Any other functions? I think you must have tried. This video is well in advance, so I don't know. I should have made the video after my lecture, but anyway, this is how I plan. So let me go through with this. So F5. F5 will be, let us say, all these 3 in a cyclic rotation. So 1 goes to 2, 2 goes to 3, and again 3 goes to 1. So you can see this is different from all this. And F6. F6, let us write 1, 2, 3. So then double jump. So 1 goes to, not 2 or but directly 3. 2 goes to 3 and 1. So 2 goes to 1 and 3 goes to 1, 2. So 2. So these are the only 6 possible functions, 1, 1 and on to functions. You cannot have any other. So in this case, if cardinality of S is 3, then cardinality of AS, we can say that cardinality of AS equals to 6, which is, uh, let's wait. Let us see. So now what about when cardinality of S equals to, so this is when cardinality of S equals to 4. What about cardinality of AS? How many such functions will be there? Then we have to list like this 1, 2, 3, 4, and then we have to try it out all these possibilities, which can be exhausting if the number of elements in S keeps on increasing. So here it is 24, and you can guess correct. And this we are going to discuss. We must have discussed last time. So this is nothing but it is 3 factorial. This is nothing but 4 factorial, right? So when the S has n elements, S is a finite set with n elements. Uh, this implies cardinality of AS. How many 1, 1 and on 2 functions will be there? It will be n factorial. I'll be giving the proof in a minute. But before that, let us together we see another notation for writing this type of function. See, all these are functions: F1, F2, F3, F4, F5, F6. They are 6 functions. But we can, because they are just 1, 1 on 2 functions. So if we have a set of n elements, its image is also set of n distinct elements, because 1, 1 and on 2. So that means it is just changing, permuting. 1 is sent to somewhere, 2 is sent to some other place, 3 is sent to some other number. So they can be viewed as permutations, although these are functions. So there is another way of writing this, those permutations. So let me write that. So F1 we can write as, so 1, 2, 3, and F1 is identity. 1 goes to 1, 2 goes to 2, 3 goes to 3. So this is another way of writing 1, 2, 3. See, this is a function itself. Like this, f of 1 is 1, f of 2 is 2, f of 3 is 3. This is a function. Right? Similarly, f of 2, f2, sorry, f2 is what? 1, 2, 3, and then 2, 1, 3. So f2 of 1 is 2, f2 of 2 is 1, f2 of 3 is 3. So 1, 2, 3 goes to 2, 1, 3. Similarly, f3 is f3 of 1. What is the image of 1 under f3? It is 3. f3 of 2, this is 2. f3 of 3, that is 1. Similarly, f4. So f4 equals to 1 goes to 1, 2 goes to 3, and 3 goes to 2. So similarly, f5. So all these 6 function we can in fact write like this. And these are nothing but we call it permutations 2, 3, 1. So here f6 is 1 goes to 3, 2 goes to 1, and 3 goes to 2. So f6 of 1 is 3, f6 of 2, at 2 f6 is 1, the image is, and if the argument is 3, f6 of 3, just like this we write f6 of 3 equals to 2, so 3 goes to 2. So this is how we write the functions. So they can be written in the form of permutations also. And now coming to this proof of this, that if S is a finite set of n elements, then the number of elements in the group AS, that is set of all bijective functions from S to S, is n factorial. So let us see this. So we start with an exercise. I'll just give you the hint of this. I'll not write the proof formally. If S has n elements, then the group AS has n factorial elements. So I'll just give you, so this is S, and we do not want this now. So S to S. So n elements. Suppose we list like this 1, 2, 3, and so on, n. Right? Now, for 1, how many possibilities are there for 1? How many functions? We can take f1 of 1, which goes to 1. We can take f2, which maps 1 to 2. We can take f3, which maps 1 to 3. So how many possibilities are there for 1? There are n possibilities for 1. Image of 1 can be 1, 2, 3, and so on for n. So 1 has n possibilities. Now what about 2? If f1 of 1 takes 1 to 1, then f1 of 2, the same function, cannot take 2 to 1, because now we are considering 1, 1 and 1, 2 functions. So if 1 is mapped to, say, let us say 5, then the same function cannot map 2 to 5. It can, what are the possibilities of 2? F, the function, the image of 2 can be 1, 2, 3, any of this n except 1. Which will not be there. The image of 1 cannot be same as image of 2. So the possibilities of uh, image of 2 are n minus 1. I hope this is clear. For 1, there are n possibilities. Any function can map 1 to any of these n numbers. But for the same function, the 2 cannot be mapped to all of this. It can be mapped to only n minus 1, except the same integer where 1 is mapped, because it is 1, 1 function. Otherwise, it will be many 1. So now, what about the possibilities of 3? So there will be image of 1 already there. Say, let us say image of 1 is 5. Image of 2 is, let us say, 8. Then image of 3 cannot be 5. It cannot be 8. It can be all other n minus 2. So n minus 2 possibilities for this, and so on. So how many possibilities for here? The last one will be fixed. Once you fix n minus 1, the last one will have no choice. So total, what is the possibilities? The total product is n into n minus 1 into n minus 2, and so on. So last one. So this product, this is equals to nothing but n factorial. So there are n factorial such functions, one and onto functions from a set of n elements to itself, onto itself. So cardinality of as equals to n factorial. So that was the exercise. So 6 already here we have listed 6. So 6 is the correct answer when there are 3. So all these 6 are there. So no other functions. So in case when s equals to 4, let me mark this cases here. 1, this is 2, this third example, and this is 4. So when cardinality of s equals to 4, it's good that we did not try. I hope you have not tried all this. Otherwise, there will be 24. And it is by trial and error, by brute force method to list all this. It will be very difficult to list all 24. We might miss something, and or we might list more than one function more than once. So that may be possible. So the cardinality of as, when cardinality of s equals to n, the cardinality of as is n factorial. Okay, so now what comes next is that we have given, as we already discussed here, this kind of notations can be used for functions, and that is one onto functions. This kind of notations can be used, which is we call permutation. So we give this notation. This is what we have described. So suppose S is the set x1, x2, xn. Suppose S has n elements and theta belongs to AS. This is also what we have discussed in the last video is also there. We have discussed in the meet also. But just before going further, let us recall this. So theta belongs to AS. So what is theta? Theta of x1. Theta of x1, it is one of this. So it is, let us call xi1, because we don't know whether x1 is x1, but it is one of this. And similarly theta of x2 also will be one of this, but it will not be theta of x1, because otherwise it will be not one function. So it will be other than this, and let us call it xi2, where xi2 is different from xi1, and so on. So theta of xn equals to xin. So we have xi1, xi2, xin. These are all n distinct elements among x1 to xn. And then how do we write theta? We can write theta in terms of permutation. We can write like this: x1, x2, xn. We can write like this is theta of x1, x2 goes to theta x2, and so on. Xn goes to theta xn, and we can also write like this, because already we have named the images of x1, x2, xn. So this is theta x1 is nothing but xi1, xi2. So all this will be distinct, xin. So this is another way of writing a one and onto functions on a finite set to itself. S is a finite set, theta belongs to AS. So theta is a one function from x1, x2, xn onto the same set x1, x2, xn. So this is how we write, and this is called permutation. And in this, with regard to this, we have fixed one notation that if we have, suppose, if we have theta and sigma, we have two functions in AS, then how do we define the composition? And how do we write in terms of permutation? So then we define the product as so both is possible. Theta, sigma composition theta, theta composition sigma, both are possible. So how do we write? So let us say sigma composition theta. So this we denote by, so this is nothing but x1, x2. So x1 goes to, first theta is applied, right? Theta is on this side in the composition. So sigma composition theta of x1. So this is nothing but sigma of theta of x1. Sigma composition theta of x2. This is nothing but sigma of theta of x2. just a standard notation which we use. Sigma composition theta at xn is nothing but sigma of theta of xn. So this is one notation, and this we denote by sigma theta. So we denote like this: sigma theta equals to sigma composition, sorry, theta sigma. So we denote this by theta sigma equals to sigma composition theta. Right? Uh, if we want to write in terms of permutation, then we write like this. We get the same permutation. If you want to write in terms of composition, then we write like this. So this is theta sigma. So theta will be like, so 1 x1. Here we have theta x1 and x2, theta x2, xn, theta xn. And then again here we have the whole sigma. Right? So when we take x1 goes to theta x1, and then check here wherever there is theta x1, where does it go? So let us consider one example in yes, and then we have discussed one special notation for this. That is also fine. Instead of x1, x2, xn, if I take 1, 2, 1, 2, 3 up to n, then as is nothing but we denote by sn. So if s equals to, let us say 1, 2 up to n. So this also has n elements. How many elements as has? As also has n factorial elements, but as now we denote this by Sn. So as is special notation when we use 1 to n. We can also denote whenever s is x1, x2, xn, we can also denote as by Sn. There is no problem. It's not that we have to take 1 to n. 1 to n જ લઈએ ત્યારે જ Sn કહેવાનું, બાકી ના કહેવાય એવું નથી. It is fine, but this is special notation. We know permutation group. You must have studied in B.Sc. Otherwise, we are going to anyway discuss here. So this is the special notation. Okay, so now let us consider an example in this notation. Especially, we are going to verify this. So it will make you clear what is the, I mean, how do we write composition and why do we write like this in the reverse order when we are writing in the terms of permutation, because we read from left to right. So as I said in the last class, here theta is applied first. X1, first we take theta of x1, then we check its image under sigma. So theta is applied first. So when we are reading in terms of permutation, we go from left to right. So theta we read first and then we read sigma. So let us consider one example. So right, so let us take s equals to 1, 2, 3, 4, 5. Let us take s has 5 elements, and so as is now nothing but s5. This is our as, right? And we take 2 elements. Let us take theta and sigma in as, so in s5, and let us fix theta. So what is theta and what is sigma? So let me divide this. Right, so let us write theta of 1, theta of 2, theta of 3. As if we write theta as a function, then we write like this: theta of 5. And here we write sigma of 1, sigma of 2, sigma of 3, sigma 4, sigma 5. Right? So let us fix some functions from the set of 1, 2, 3, 4, 5 to itself. So let us have theta 1 equals to, let us say 2. This let us take 4, and this 5, and 1, and whatever is left, so 3. Okay, so theta is this, and sigma, let us consider sigma of 1 equals to 4, sigma of 2 is 2. Let us say if the sigma fixes 2, then sigma of 3, let us take it 5, and this is 3, and this is whatever is left, 1. So 1, 2, 3, 4, 5, all 5 are there. 1, 2, 3, 4, 5, yes. So this we have fixed. And now let us first compute sigma composition theta. Sigma composition theta. So sigma composition theta of 1, sigma composition theta of 2, sigma composition theta of 3. And let me pause here, write this, and then we'll continue so that video is shorter. Right, so I have written, I paused this video and I've written all this so that you don't have to wait to see me writing all this. Oh, but the idea ધીમે ધીમે આવે, પહેલા lecture ના આવે. Anyway, so let us compute this. Sigma composition theta of 1. So theta of 1 is 2. So this is sigma of 2. And sigma 2, what is sigma 2 is 2. So this is 2. Sigma composition theta of 2. So theta of 2, theta 2 is 4. This is sigma of 4. Sigma of 4 is what? Sigma of 4 is 3. Actually, I'm pointing finger, but my finger to dekhase nahi tamne. I have to point this. So sigma of theta of 3. Theta of 3 is 5. So sigma of 5. What is sigma of 5 is 1. And theta of 4. Theta of 4 is 1. So sigma of theta 4. So that is theta 4 is 1. Sigma of 1. Sigma of 1 is 4. Good. And then sigma of theta of 5. Theta of 5 is 3. So sigma of 3. Sigma of 3 is 5. Okay, so we have this. Sigma composition theta. Now the same thing, I am writing this function in place of in terms of permutation. So how do we write? 1, 2, 3, 4, 5. And sigma also we can write 1, 2, 3, 4, 5. So image of theta. Theta of 1 is 2, theta of 2 is 4, theta of 3 is 5. So we can write directly like this: 2, 4, 5, 1, 3, as you can see. And sigma 4, 2, 5, 3, 1. So this is how we write function. This is also function, but in terms of this permutation notation. And let us now compute sigma composition theta. So here the theta was on the right hand side. Now here the theta is on left hand side. So first we are computing theta of, so what I write here, theta sigma. See here there is no composition. The composition here, sigma composition theta, here we write theta sigma, because theta we read first from the left hand side, then we read sigma. So theta of 1, see, theta of 1 we read first, that is 2, and then we applied sigma. So here we read theta of 1, so 1 goes to 2, and then sigma sends 2 to 2, so finally theta sigma will be 1, 2, 3, 4, 5. 1 goes to 2, 2 goes to 2, so 1 goes to 2, and you can see 1 goes to 2, right? So theta sends 2 to 4, so theta of 2, here theta of 2, that is 4. So theta sends 2 to 4, and then sigma of 4 is 3. So 2 goes to 4, 4 goes to 3, so 2 goes to 3, right? Is it clear? So 3 goes to 5, 5 goes to 1, so 3 goes to 1. 4 goes to 1, 1 goes to 4, so 4 goes to 4. 5 goes to 3, 3 is mapped to 5, so 5 is mapped to 5. So what we have? 2, 3, 1, 4, 5. 2, 3, 1, 4, 5. Yes, full marks. Not full marks, half marks, because still we have to compute the other product. So now similarly, I hope you will be doing this. What we have to do now? Theta composition sigma. So theta composition sigma. So let us compute. Let me write this. By pausing the video, first let me write this. You can check yourself. I'll write all the calculations so that video does not become larger in size. Okay, so now here I have written all this. So theta of sigma of 1. So first we read sigma. Now this is theta composition sigma. So first we read sigma. So sigma of 1 is 4. So theta as it is, and sigma of 1 is 4. Now we read theta. What is theta of 4? Theta of 4 is 1. So this is 1. Similarly, theta of sigma of 2. First we read what is sigma 2 is 2. So this is 2. And then theta of 2. Theta of 2 is 4. So this is 4. So let me write the rest of the entries. Yeah, so I have written all these entries. I hope you also verify with pen and paper. So, and make sure that all this are distinct, because these are 1, 1 onto functions. So composition is also 1, 1 and onto. It is a group we have just shown. So 1, 2, 3, 4, 5, all 5 are there, all are distinct. Now, when here we are computing sigma composition theta, what here on this side we'll write, if we write in place of permutation, what we write? We write sigma first. So we write sigma first and then we write theta. So let me write sigma 1, 2, 3, 4, 5. I copy this sigma here. 4, 2, 5, 3, 1. And here I write theta 1, 2, 3, 4, 5. And what I copy this 2, 4, 5, 1, 3. Remember? So this is theta composition sigma, but in this composition sigma is applied first and then we apply theta. So but when we are reading from in terms of permutation, when we are reading, we read from left to right, and so we write sigma first because here sigma is applied first, and then theta. So what is sigma theta here? So 1, 2, 3, 4, 5. So 1 goes to 4 sigma and then 4 goes to 1. So 1 goes to 1. 2 goes to 2, 2 goes to 4, so 2 goes to 4. 3 goes to 5, 5 goes to 3, so 3 goes to 3. 4 goes to 3, 3 is mapped to 5, so 5. 5 is mapped to 1, 1 is mapped to 2, so 2. Here also you can check all this must be distinct. Here 1, 2, 3, 4, 5. Here also they must be all 5 distinct. So we got 1, 4, 3, 5, 2. So we have 1, 4, 3, 5, 2, and yes, we are done. And you can see here what important thing we have observed is sigma theta is not equals to theta sigma. So they do not commute. So the question whether AS is an abelian group or not, AS5 is non-abelian group. We have found an example like this. You can create another example also such that they do not commute. So sigma theta is what? So that is sigma theta is nothing but sigma theta sigma is nothing but sigma composition theta. This is not equals to theta sigma is both I have written theta sigma only. So sigma theta is not equals to uh, yes, theta sigma is not equals to sigma theta, but theta sigma is same as sigma composition theta, and sigma theta is nothing but theta composition sigma, so they are not same as you can see. And this 2 3 1 4 5 2 3 1 4 5. So when we are writing in terms of composition of two functions, we are writing like this, but we read from left to right. So when we write in the terms of permutations, this is the notation. So don't get confused. So don't put here composition. Now this is the different notation, this is a different notation, but what we mean from here is this. What we mean from here is this. So permutation we read from left to right. So this is a standard convenient notation. Okay, so this is all about the previous lectures, this last Google Meet. And now we come to a very special example, that is of S3. Only 3 elements, not 5. S3, and that is very standard example. Let us see. Okay, so now let us consider the standard example of S3. So we construct S3, which is so we know this Sn. They are called symmetric groups. Why they are called symmetric groups? We'll just see in a moment. Before we construct S3 like this. So how do we construct S3? So we have S3 is what? 3 elements. We can take A, B, C. We can take x1, x2, x3, but we take 1, 2, 3 here. So that we can write it as permutations, those functions. So S is 1, 2, 3. And what is S3? S3 is nothing but it is actually AS, set of all 1, 1 and 1, 2 functions from S to S. So AS, how many elements it has? If S has n elements, AS has how many elements? N factorial, we have just seen. So here it has 3 elements. So how many elements it has? 3 factorial, so 6. So we have 6 functions. So this is an equilateral triangle. Uh, I hope this is equilateral triangle. There is a little bit problem. I did not draw by exact measurement, and we have labeled its those angles, corners, vertices as 1, 2, 3, and we read them in the clockwise. Uh, sorry, yeah, we read them in anti-clockwise direction. So 1, 2, 3. So this is how we read. So S3. So 3 elements are there, 1, 2 and 3. And now in how many ways we can rotate or flip or do something with this triangle such that the figure is also exactly the same. It fits into this border. This border you can see, the black border. So it fits into that. For example, if I rotate this triangle by 90 degree, as you can see here, there is an option for rotation. So let me write 90. I hope you can see here at the bottom. There is this 90-degree rotation, and let me press enter. So this triangle is rotated by 90 degree, but if I try to fit in the frame, you can see it does not fit. So we have to do rotation flipping in such a way that it again set back in the frame. So 90-degree rotation is not possible. So how much degree rotation is possible? So one is that so there are three angles. So three angles, so 360 by 3, so that is 120. So 120 and in multiples of 120. So 120-degree rotation of this triangle will give us same triangle. So same shape, because it is equilateral, it will sit inside. Then 240-degree rotation also will give us the same shape. It will fit in the frame. And then again 360-degree rotation. So one thing what we do is that we don't do anything, no rotation at all, 0-degree rotation. If we give 0-degree rotation, that means the triangle is as it is. So how do we read from this? 1, 2, 3. So that is nothing but it is our identity map. Anyway, we know one map, which is E equals to 1, 2, 3 is 1, 2, 3 as it is. So the triangle is left as it is, no rotation, nothing. Or 360-degree rotation. If we rotate the triangle by 360 degree, then there is nothing, it will be the same structure, right? Yes. Now let us rotate it by 120 degree. So here is an option for rotation. I hope you can see. So let me type 120, and now if I press enter, so the triangle, because of it's not equilateral triangle and it's not rotating about the particular point where I wanted, but it is, you can see I can drag, and yes, it fits inside this shape. So now what has happened? 1, 2, 3 has become 2, 1, 3. The position has changed, 120-degree rotation. So it has 1, 2, 3 has become, when we start reading from here in the anti-clockwise direction, so it has become 1, 2, 1, 2, 3, 1. So we have one rotation. Let us denote that by psi. Psi equals to 1, 2, 3. What has become of 1, 2, 3? 2, 3, 1. And this is rotation by 120 degree. Now again let us rotate the same figure by 240 degree. Then also it will sit in the same frame. So let us rotate by 240 degree. I hope you can see here. I am not able to zoom it. So this is 240 degree. Now I press enter, and now let me bring this into the frame. Yes, it sits into the frame, and this has become 3, 1, 2. So rotation by 120 degree, then 240 degree means again rotation by 120 degree. So again rotation, that means this is we can write this as psi square, right? Because this is rotation by 120 degree, and this is again rotation by 120 degree. So psi to psi, 120 and 120, so 240 total. So this has become 1, 2, 3 has become 3, 1, 2. Yes, this is 3, 1, 2. And then what happens if we rotate this again by 360 degree? So here, yeah, 240 is there. So let me rotate it by 360 degree, and let me drag here. So 1, 2, 3. So 360 degree, again it comes back to the same position, 1, 2, 3. So that means what do we have? Psi cube equals to 1, 2, 3. Again we got 1, 2, 3. So psi cube equals to, again we are back to identity. So there is rotation. What else is possible? So we have rotated by 120 degree and 240 degree. What if we rotate in the other direction by 120 degree? Other direction means minus 120 degree. Let us try to see the rotation minus 120 degree. Now it is 1, this is 2, and this is 3. Now let us try to rotate this by minus 120. I hope you can see this is minus 120.0, and let me press enter. So the rotation has minus 120 degree is possible. So that is 120 degree is psi. So minus 120 degree is the inverse of psi, because when you rotate by 120 degree you get psi, and then we rotate back minus 120 you will get identity. So this is psi inverse. So what is psi inverse? 3 1 2. So psi inverse is 3 1 2, and let us see. So suppose this is 120 degree rotation, this is what, 240 degree rotation, and so minus 120 degree rotation, what was minus 120 degree rotation? 312. But 312 is this, so this is same as minus 120 degree rotation. That means this guy psi square, this is same as psi inverse, and this is will be same as minus 240 degree rotation, and so that so this will be same as psi raised to minus 2, minus 240, you will get this, and that is true because psi cube is identity. So psi cube is identity, this means psi square, this is identity. So inverse of psi is what? It is psi square. Here psi square, that is inverse of psi. So this is one such possible rotation, symmetry due to rotation. And now flipping. So let us try with flipping. So let me bring back to 0 degree. Yeah, so this was our original triangle, 1 2 3, and now what we do is we flip this triangle. So this is flipping, so this is horizontal flipping. So what will happen? 3 will remain as it is, this part will interchange, 1 and 2 we flip. Flipping means like this is called flipping. So this is the front side, and if I do like this is called flipping. So 3 will remain same, and 1 and 2 will interchange. So let me click here, and you can see. Did you observe? You can go back in the video and check. So 3 as it is, and 1 and 2 has interchanged. So 1 2 3 has become now 2 1 3. So let me denote that element. So that is called flipping. So denote that by 5. 1 2 3 has become now 2 1 3, and so this is flipping. Yes, so now let us see what happens if we flip back. Now this is 2 1 3. I click this and I again flip back. See what happens, right? So if I flip this again, I flip back, what happens? 1 and 2 are back in the position. So now it is 1 2 3. That means if I flip twice, then I get the same position. So that means if I take phi square, so phi square, this is identity. So phi square, this is identity. That means inverse of phi is phi. So flipping back, that means phi inverse equals to phi. Phi square equals to identity. And we can also check this phi square. What is phi square? Phi into phi. So how do we check? We write 1 2 3, and phi is what? 2 1 3. 2 1 3. Again same element, phi into phi. So 1 2 3 and phi, so 2 1 3. And now check this. So 1 goes to 2, 2 goes to 1, so 1 goes to 1. Then 2 goes to 1, 1 goes to 2, so 2 goes to 2. Now 3 goes to 3 here, 3 goes to 3, so 3 goes to 3. You can see this is nothing but identity. So phi square is identity, psi cube is identity, so this has order 3, order of element we are yet to define, but you know already because you have done in the B.Sc. So psi cube is identity, phi square, that is flipping, that is identity, and so inverse of psi is nothing but psi square. and inverse of phi is nothing but itself, it's order 2, right? And so what else is remaining? So let me wipe out this, and then we can check what else is remaining. Yeah, so what other possible options are there? We can use the combination of this two. For example, we can rotate first by 120 degree and then flip. Then also we get the same triangle which sits in the same frame. We can flip first and then rotate. So let us try to see what happens. So let us first rotate this. So I take the rotation, I take 120 and I rotate this. I got a triangle. Yes, it sits in the same frame, and then I try to flip it. Flip by, so this is the symmetry, and so pardon me for this because I did not write the numbers very well, and this flipping is not about particular axis where I want it. So what we have got 3, 2, 1. So what we have done here, we first rotated and then we flipped. So rotation is this 120 degree rotation. So psi, and then we flipped, and what we got is 3, 2, 1. Yes, you can see here 3, 2, 1. So phi psi is 1, 2, 3 is mapped to 3, 2, 1. Similarly, we have first we flip, so phi, and then we rotate, so psi. So let us see what do we get if we first flip and then rotate. So let me bring back to this original position. Yes, now 1, 2, 3. What we do first is we first now flip. So I consider flip first. So 1 and 2 are flipped and 3 is as it is. And now I consider rotation by 120 degree. As you can see here, rotation by 120 degree. What do I get? I get 1, 3, 2. Right? So I get 1, 3, 2. Yes, so we have got so far 6 elements. And what else? Here I've rotated by 120 degrees. Somebody would like to consider psi square and phi. So rotate by 240 degree and then flip. Let us try that. So let me bring back to the original position. 1, 2, 3. Yes, 1, 2, 3. So what we do, we rotate by 240 degree, let us say. So this is 240 degree rotation happening. Yes, I bring back to this frame, and now let me flip. Okay, so I have 1, 3, 2. So rotation by 240 degree and flipping back 240 degree means psi square and then phi. And what I have got is 1, 3, 2. 1, 3, 2 reading like this in the counterclockwise direction. So so this is the same. So this is nothing but rotation psi square and then flipping rotation by 240. So psi phi is phi psi square, and similarly here also uh, phi psi will be psi square phi. And so these are all only the possibilities. And where we have seen this? We already seen the 6 functions. So this is actually what we have seen S3, that is AS, when the set has 3 elements. That is the reason I did not write there ABC. As you can see here, cardinality of S equals to 3. If I had written ABC, I would have got in ABC. That's just notation. So that this has AS has 6 elements. So this is F1, which is identity for us. Then F2, 1, 2, 3 goes to 2, 1, 3. And so this is nothing but this is our F2, 2, 1, 3. This is F2, this is F1, this is F3, 2, 1, and then 3, 2, 1, and then 1, 3, 2. 3, 2, 1, 1, 3, 2. So this is F3, F4, and F5, F6. So F3, this is our F4, this is F5, and F6. So it is the same example AS. So that is the reason I did not take their ABC, because I wanted to relate with this. So this is the gives a symmetry of triangle. All these operations, rotation and flipping by that center by angle bisector axis. So you can try all this. These are the only 6 possibilities are there. So this is the standard group, and the reason why I have used here e, psi, phi, psi square, because these are the standard notation. It will come in the second unit also. So for S3 we fix this notation. So consider this as an example for S3. Okay. So finally, if you want to write S3, this group we can write as identity element, as the group always has identity. Then phi square equals to, so if we multiply phi again identity, then psi, if we multiply psi with psi we get psi square. If we again multiply psi cube, again it is identity. So then this combination phi psi, this is non-abelian group. Phi psi is not a same as psi phi. You can see one goes to 3 here, one goes to 1 here. So phi psi is not equals to psi phi. So this group is not abelian. What is abelian group? If AB equals to BA for every AB in G, then the group is abelian. So phi psi, and then so there is another combination psi phi. What about phi psi square? Here, phi psi square is nothing but psi phi. So it is already there in the group. And similarly psi square phi is this. So all only 6 elements, only all the 6 elements, and this is a standard notation we fix all throughout this course, phi and psi. In case of S3, these are the notation. Okay, so now let us go to the definition of a cyclic group. So you know what is a cyclic group? If it is generated by one single element, then it is called cyclic group. But let us define like this. So let n be a fixed integer and g equals to, so g is a group which is of this form. Identity we denote by a raised to 0, then a raised to 1, that is a, then a square, and so on up to a raised to n minus 1. So what is a raised to n minus 1? A into a into a into means not the product, but a dot a dot a, or a star a, whatever the binary operation of the group is there. So this is just symbols, a raised to I. So where a raised to 0, this is identity, this is a raised to 0 is same as a raised to n again is identity. So this is what we define, fix the symbols. And for these symbols we define a raised to I plus a raised to I into a raised to j. What is that? So we define the symbol a raised to I, a raised to j. This is how do we define? Usually we define like this, a raised to I plus j. But this we define only if I plus j is less than n, because you can see we have only n symbols, a raised to 0, a raised to 1, a raised to 2, a square, and so on, a cube, a raised to n minus 1. So if it is strictly less than n, then we define like this. What if the sum is greater than n? So this is a raised to I plus j minus n if I plus j is greater than equals to n. So if it is n or it exceeds n, then we define like this. So then this is an exercise for you. As usual, when exercises start coming, the lecture is going to end. You can clearly make out. So exercise that G is a group with this operation. So a raised to I, a raised to j, that binary operation is defined like this. This is a group and it is called a cyclic group of order n. So you have studied this in BSc, it's called, but even if you have not studied, so everything is just revision. But whatever you have studied, that part I will not go too much in depth because this is an advanced course, but all basic concepts are there. So it is called a cyclic group of order n. What is order? Order is nothing but if the group is finite, then the number of elements in the set, that is called order of group. So it is called a cyclic group of order n. And we denote sometimes like this, g equals to, it is denoted by a. Sometimes we denote just like this. That means g is nothing but this. It's generated by single element a. So the whole powers of a square, a cube, up to a raised to n minus 1. then a raised to n is nothing but it is identity. So the cyclic group of order n. So that is one exercise. This first exercise for the next class, and this you need not show me. This is just for your practice. Another exercise, we have considered the group AS. So it is related to that same thing. So another exercise is consider S equals to the set of integers Z, and we consider G. It's a subgroup of AS. So we consider uh, all sigma belongs to AS such that sigma of n equals to n. Sigma of n equals to n for all but finitely many. For all but finitely many n. Finitely many n belongs to Z. What does this mean? This means that sigma fixes everything except finitely many integers. So Z, S equals to Z, the set of integers, and G is nothing but G is subset of AS. AS set of all 1 1 onto functions from Z to Z. Not all 1 1 onto functions, but all those functions which fix n, all n except finitely many. का तो एक में चेंज हुए का तो बे नंबर इंटरचेंज करे और 3 or 4 whatever, that not only interchange but whatever that I mean, it is not except for finitely many, it is just like identity function. So identity is also there because identity does not change anything. So we have to show that this is a subgroup of AS, or subgroup we have not defined yet, but anyway this is subset of AS. So what we have to show, G is group, G with composition is group. That is what we have to show. So these two are exercise, and let me first, before proceeding further, let me give a geometrical realization of cyclic group. So geometrical realization of cyclic group. So consider unit circle. Okay, this does not look like circle anyway. We are mathematicians. We assume this is a circle, right? And we consider rho n. So rho n, what is rho n? Rho n is rotation of points. So this unit circle is denoted by S, and rho n is rotation of points of S by an angle of 2 pi by n. So 2 pi is the total angle, and rho n is the rotation by an angle 2 pi by n. Then what is, then G equals to this is the group E, then rho n square, and so on, rho n power n minus 1, right? So this is the cycle. So this is rotation by 2 pi by n, then 4 pi by n, it's square, and so on. So this is a cyclic group of order n. In particular, if we consider some example, let us say rho 4. So rho 4 is what? It is rotation by 2 pi by 4, that is nothing but pi by 2. So it is just 90-degree rotation. So if there is a point here where it will be mapped, it will be mapped here. This is rho 1, rho 4, then rho 4 square, that is nothing but so this is rho 4. Rho 4 square, it is 90 degree and 90 degree. So this is rho 4 square. This entire thing from here to here, this is rho 4 square, that is 180-degree rotation. And then from here to this point, if it comes here, this is nothing but rho 4 cube. And then so again back here 360-degree rotation. So that is identity. So If a point is here, then it comes here. So let me draw it with another color. So if the point is here, then 90 degree. So row 4 will bring here, then again 90 degree. So this will row 4 square will bring here. This is row 4 cube, and then again here. So 90 degree rotation. That is then we have a group of 4 elements. Identity, that is no rotation at all. 90 degree rotation, 180 degree rotation, 270 degree rotation, and then again identity. So this is cyclic group, just geometrical. So it maps points of S to points of S by just rotations. So these are the two exercises, and finally let us go and do some more elementary exercises. Yeah, so here these are all the basic results which we have seen in BSc. Anyway, if even if you have not seen, these are very basic results. Prove that identity element of group is unique. If you cannot do it yourself, if you have not seen in BSc, seeing it for the first time, anybody, I really doubt. Uh, but if that is the case, then I suggest you refer very elementary books on group theory, and you will get this exercise. But first, try on your own. Inverse element is unique. Inverse of A inverse is A, and AB inverse is nothing but B inverse A inverse, and then the cancellation laws. So A, B, and G, then the equation AX equals to B, YA equals to B have unique solutions for X and Y, and in particular the cancellation law holds. Cancellation law means this is left cancellation. AU equals to AW. This implies A cancels on the left, so U equals to W, and this is the right cancellation law. UA equals to WA. A is cancelled on the right hand side. You get U equals to W. So these are all preliminary lemmas, and so that is left as exercise. Even in Hurston book, that is left as exercise. But these are very trivial exercise. So I think I should stop here. I'll give you the notes when it will be ready. I don't know whether it will be ready or not, but anyway, I'm writing everything here on my video. So everything is there on my video. I am also giving you the PDF file of whatever I have written in my video lecture notes. So you have notes with you. So no, don't worry about this notes. Anyway, I'll give you once they will be ready. Maybe while I teach, I'll try to correct if there are some mistakes, or if there are any modification. I'll try to do that, and then we'll send you by the end of the unit. So, and as you can see, I'm covering some syllabus here in every lecture. So be prepared every lecture, watch the video, and come in the next meet. You might need to work out some exercises on your own, try to solve some examples. If you have doubts, we are going to discuss in the meet, and if you have further doubts, we can discuss in the Google Classroom also. So thank you.